I think I'm back. Can you see? Can you see the feed? Just let me know. And I'm looking on two screens. Looks okay?
I think I'm back.
I'm gonna move the microphone away from the stream. It's so loud. The computer's so loud. Okay, let's see if this works. All right. So yesterday we left off talking about the confidence interval. So this is known as the C% confidence interval. This is the formula. So what it is an interval that's an improvement upon just using the mean in this case. Well, I know this is a proportion, right? This is a sample proportion. So I want to estimate the sample proportion. The best guess at, sorry, I want to estimate the true proportion. The best guess of the true proportion is going to be the sample proportion. The sample proportion is just one value. It's just one value computed from one sample. That sample comes from a set of all possible samples. And we discussed the theory behind what that distribution of that sample would look like. So from that, we know that so if we just go up on our formula sheet to remind ourselves, it's all here. You just gotta repeat, go up, convince yourself that we know this already. So we know that for the sample proportion here, that is the proportion of successes out of an independent trial. So that's the results of a sample where you're just looking for a certain outcome versus the alternative. You know that distribution is approximately normal as long as this condition is satisfied, and we say the population is large. Population large means that the population size is greater than 10 times the sample size, okay? So that's what we're going to use for large. And so this is the mean, and this is the standard, sorry, this is the mean, and this is the standard deviation. So let's say that the mean of the distribution of all the sample means is has a mean of, sorry, the mean is P, the true proportion, so the expected value is the true proportion, and this is its standard deviation. The shape of that distribution is normal approximately as long as these conditions are satisfied that make the binomial distribution look normal. Okay, so there it is. That's the mean, that's the standard deviation. So what I'm doing is I'm computing an estimate for P. So this is inference, I called it inference on P, where P is unknown. Inference meaning educated guessing. Okay, we're going to guess using the evidence from a sample. What would P be? So the best that we have is the sample mean, and then we're going to create an interval around that. And we know how to do that because it's normally distributed. We just do this plus and minus, right? Plus and minus what? 1 standard deviation, 2 standard deviations, 1.5 standard deviation, whatever we want. That's what the Z star represents. What do I want? In this case, what I want is an interval that covers 98% of the middle observations. So to get 98% of the middle of observations, I found I could use the I'm kind of recapping what I said last time. So if I want 98% in the middle, that means there's 1% out here and 1% out here. All I want to know what I'm interested in is this. This is my Z star. This is my Z star, but this one would be negative and the other one would be positive. So we looked that up for 98% and we found that 2.33, that's how precise we could be, 2.33 standard deviations from the mean would put 98% of the observations in the middle. So that's the number I'm going to substitute there. So that's what we did last class. So I'm going to go back to page 4. And we agree that the best answer out of the options for 2.33 standard deviations was B. So it's very important. I'm going all the way back to the second unit of this course, hoping that you remember that we learned how to create an interval for a normally distributed variable, right? Using the mean as standard deviation to create like an estimate around the mean. And okay, so I left off saying this is not exactly 2.33. Where did this number come from with 3 decimal places? That's what I want to show you now. So this comes from, I'm going to go back to the end, going forward, and I'm going to introduce you to this table. This is the first introduction. This distribution is symmetric, bell-shaped, single-peaked, but it's not normal. Well, it's not always normal. Let's say it like that, okay? This table represents, actually, it's inverted in that inside the table you find the t-scores, whereas in the z-table you find the z-scores on the margins on the left-hand side. And I'll just show you, right? So here are the z-scores. They're on the margin, but on the t-table, these are the t-scores. And the probabilities, whereas in the z-table, the probabilities are inside the table. For the t-table, the probabilities are on the top here. So I'm going to spend more time later explaining how you use this. All I just want to do right now is orient you to look here. The t distribution depends on the sample size. Okay, so it's a distribution for samples. Okay, so the sample size is going to determine which row you take. Now you can trust me on this, or you can have a closer look. What's going to happen is the first few distributions are going to be much more flat. Okay, so we call them large tails because they're going to be more flat. Okay, so like that. But as the sample size increases, the t distribution begins to look more peaked. And you see this tail here, this wider tail, like more outliers really, right? This is allowing more outliers. But as the sample size increases, there's less outliers, it goes more narrow, and in fact, the larger and larger the sample size. Now, why am I saying sample size, but this says DF? Remember what DF is. DF is df is n minus 1, the degrees of freedom. The degrees of freedom. So if we go all the way down, what we're doing is we're going for larger and larger samples. So this is a sample of size, let's see, this is a sample of size 2, this is a sample of size 3, okay, and so on. So the very bottom, what do you see? Samples of size 101, samples of size 1001, and you see across the way here is not so different than across the way here. So again, these are t-scores. These are how many standard deviations you are from the mean. And at the so what you have here in this row is a z star, you see? So that's where I got my value. Let's see which one I had. I had 2.326, right? 3.326, that was here, you see? That's the one that was in the problem. So it's to 3 decimal places. What's happening is that the t-distribution for large samples is the same as the z distribution. So I'm going to use just this part of this table right now. I'm not going to use the other part of the table yet. Just this lower end. So we're going to familiarize ourselves with this border, or the bottom of the table. And here's where I take that. So 98% on the z table, right? In the z distribution, 98% in the middle means that I am, just to be more precise, rather than 2.33, it's going to be 2.326 and 3.326 above. So that's below and above. Okay? Away from the mean. So that's what I'm going to use as my for my critical values. That's what I call those. Alright, so those are critical values. Alright, so we're going to do a lot of confidence intervals. This is your first look at it. The main thing, you can use these formulas, but how you know which formulas to use is to be aware, to be cognizant of whether you're looking for a confidence interval of a variable that measures proportion, in this case, or not. Okay, so for proportions, this is the formula that we use. So to recap, this is the formula. Let me make it so you can stare at them together. The formula is p hat plus or minus z star, depending on the confidence interval you want. We call it a confidence interval, but it's what percentage of observations we want to capture, and the standard error. Remember, I told you we call this not the standard deviation, but the standard error, because we're using an estimate to compute it, the estimate of p hat for p. And that's that. This asterisk is supposed to be a multiplication, so don't let that confuse you. I hope that doesn't confuse you. This should be like multiply. Okay? All the way down. Any kinds of questions like that on a test or a quiz, just let me know, because maybe you haven't seen. You might, anyway, if you're nervous, those things like that might stump you. All right? So let's see. Let's go on to the next thing. The next thing, let's go back to the formula sheet. I should probably move the formula sheet closer to this. But okay, so let's move over on the formula sheet that I asked you to keep beside you as you go through the remaining of this course. Keep that formula sheet at your side so you can always refer to it and reinforce your understanding, synthesizing new information with the old information. Oh, so sensitive. Okay, so this is the next formula. This formula, whereas this was the confidence interval, we call it the C percent, in that case 98% was the one we computed. That doesn't look so good. I'm just going to write C percent confidence interval, okay? This is called sample. You know what? I'm going to make it bigger. This is referred to as sample size estimation. What are we doing here? Wouldn't it be great if we had an approach to help us determine what sample size we need? What sample size should we use to draw a sample? If you don't have any prior information, I'm going to show you how to do this if you have no prior information. I'm going to show you how to do this if you do have some prior information. First of all, though, where does this formula come from? It comes from this one. There's the N, there's the P's, but how am I using this one? There's the Z. This part of the formula maybe I'll clear all this out before I continue. I'm going to no, that's overkill. So one thing to realize is that this is the confidence interval, this is the point estimate, this is the critical value, and this is the standard error. Okay, so that's one way to look at this. So this is the point estimate. So just a single value estimate. I'm referring to the p-hat. Z star is the critical value. So that's 2 or 3 or 2.3 standard deviations from the mean. And this is the standard error. And I keep repeating this because whatever we're trying to estimate is going to use the same, we're going to use the same general approach. Point estimate plus or minus critical value times standard error. This piece that I've squared off also has a name. Anybody know what that name is? this part that I've squared off that I want to erase. So this piece make it cleaner. Okay, so this piece is called the margin of error. This is another name for the give or take, right? Remember how we always talked about that? If we would say, you know, X bar, you know, we'd say the mean plus or minus, or we'd say on average $8 was spent, give or take. This is the give or take. In statistical terms, that give or take is called the margin of error. So we're going from the less formal to the more formal language, but we're talking about the same thing. Okay, this is called the margin of error. Now we're using the margin of error in estimation. You can pre-specify the margin of error, and that can help you to determine what kind of sample size you want. So basically you're saying you're limiting. By picking the right sample size, you can create the width of the confidence interval that you want, or the confidence level that you want to achieve within a certain margin of error. So what I'm going to do, because that's also predetermined, right? So this one, so what you have power over here is you can pick the confidence level. That's you can choose that in advance before you take the sample size, and you can well, you don't know what p star will be, or p hat, so that's depending on the sample that you've had before, or if you have no information, I'll show you what to do. But what you really want is this. So you want to set the margin of error, you want to set the confidence interval, and you want to solve for n. That's how we derive this formula. So everything on the right side is given either from past information or from, so if you have no past information, you let your p star be 50%. Okay, so even if you have no information, you just go in between, go midway, right? We're used to that. Our best guess usually is right in the middle. So let's just go in right in the middle of all the possibilities between 0 and 1 for p, the proportion, the true proportion that I want to estimate. And let's just use 50%. So I'm going to use that. Let's say I have information from some other studies that were done well, or they're old, or someone's given me the information about another study and it's been recent, and you just want to replicate it for yourself in your part of town or your country, or you can just imagine maybe you have some information from the past. So if you have that, we'll say or p star equals p hat from other studies. You always hear about that, well, studies use information from other studies, so new information is updated, right, based on what people have seen in the past and new information. Okay, so the critical value, the confidence interval you want to derive, you determine that in advance. The margin of error, someone will specify that, or you'll specify what kind of error, what kind of give or take you want to leave to your confidence interval, and that depends on having no information or some sort of prior information. So what am I talking about if you didn't understand any of that? So first of all, let's derive the formula, Then we'll solve a problem using the formula, and then maybe you'll have a better sense of what's going on here. So back to page 4. So here I've left some space for you to derive the formula yourselves. So use this space. Here's the margin of error. I've left the hats in there. You understand, in the case that I have some prior information, I can just use p hat. If I have none, I'll replace it with p star of 0.5, right? So let's solve this for n. Algebraically, we'll say given someone, whatever, z star, so someone tells you what to use, or you decide, you make an executive decision what you would like to use in advance. And what you want to figure out is, for this level of confidence, to be able to estimate a confidence interval with a certain level of confidence and a particular margin of error, and using some prior information, or just 50% as my p hat, what sample should I take? So let's see if we can solve this. So if you like, turn off the video and try it yourself. Otherwise, I'm going to solve it right now. So what you can do algebraically to solve this, to isolate n, is first take z star down, and that'll give you this. And now you can see where that square power, if you notice, this is where it comes from. I'm going to square both sides. Okay, and so now you're starting to see where the formula comes from. Now what I'm going to do is, algebraically, I can solve this by multiplying both sides by n and dividing both sides by m over z star squared, which works out to just like flipping these around. This one goes here, and that one goes there, right? That one goes up, that one goes down. And when this fraction goes down here, it's the same as multiplying the reciprocal, so it gets flipped as well. All right, so what does that look like? Lots of steps here. So if you have to review it after I finish the video. So this is going to go up here. This is going to be here. And in front, I'm going to put z star over m squared and a hat. Okay, so that is the formula that's nicer or to look at down below, up above. I'm going to erase there. Okay, so that's where that comes from. Now again, you're going to say, oh, but it has hats, why doesn't it have stars? Well, like I explained, if you have prior information about what the proportion could be, you can use it here. If you don't have information, you just put 0.5 in there. So let's apply this formula so you know what I'm talking about. Compute the sample size n required to obtain an estimate of p within a certain margin of error m, or with a certain width 2m. I'll explain that as the problems arise. With C star level of confidence, use the margin of error formula and isolate for n. So we just did that. Okay, so I like to think of this formula I solved it here, and I made some points. I said if we are told P, then just call it P. So if somehow you knew what P was, theoretically, I mean, that would be the best number to use in there for your sample. But that's not very realistic. Usually you don't know P, that's why you're estimating P. But it's important to point that out. If P is not given, and there is a simple random sample available with evidence that P is not 0.5, then you should use that one from that sample, that sample proportion that was computed from another sample. If you have no prior information, just use P star equals 0.5. So here's an example of how to apply the formula. This example, suppose that we wish to estimate the proportion of Canadians who actually understand the Constitution of Canada. What is the approximate number of Canadians who need to be sampled so that a 95% confidence interval has a width of 2 percentage points? All right, so we're going to estimate the proportion of Canadians who understand the Constitution. Proportion. So this is a problem for proportion. And I want to estimate the sample size. So those are my keywords. Proportion and approximate number. So you want to get N. So that's how I know to use this formula. So taking my formula, N is, so you get to use the formula sheet, but if you had to memorize it, call it the Mazda formula. This is the zoom formula. Z over M twice. And then P star 1 minus P star. So how do we plug this in? Do we know everything? Oh, this is Z star. Do we know everything? Okay, what do we know? What's Z star? What's Z star? What's M? What's P star? That's what we need. Well, Z star is for a %95 confidence interval. So where do I find, how does that help me? I want to make a 95% confidence interval, so I want to capture 95% of the observations within, centered around the mean. So I want to know how many standard deviations I have to go away from the mean to capture 95% on the normal distribution or standard normal distribution. So I'm going to go to the best table for that, and I introduced today the bottom of the Z table, and that actually, for 95% confidence level, as it says here, I pick this one, 1.96. Okay, so I'm going to use that. I could also find it in the Z table. I could say I want to find where there's 95% here. Where would I have to be for 95% in the middle? So we know that, right? It should be 2 standard deviations, but we want to be more precise than that. Those are just, those are rounded numbers that comprise the rule 68, 95, 99.7%. So we know it should be 2 standard deviations, but let's just verify. If it's 95% in the middle, then what should the Z be for that? It should be 2.5 on this side, 2.5%, and 2.5% on this side, right? So what I'm going to look up is 0.00, not 0, 0, 0, 2, 5, 0, and see what it gives me. So I actually have to go to the negative table for that after I've drawn all this. So let's go look for 0.0250 inside of the table. And you know where I'm going to go? I'm going to go right for 1.96 because we have been shown, you see, there it is at 1.96. So I can use either the Z table or the T table for this. It's obviously easier on the T table that I taught you. However, on the T table, you don't have all the values. You don't have as many values as you do on the Z table, do you? You just have this. So you're restricted to making confidence intervals of these levels. If I asked you to create a confidence interval of something, the confidence interval of an estimate that wasn't one of these, like 97, for instance, it's not here, then you have to use a Z table. Is that all right? So we know it's 1.96. Let's go back. I wonder if there's a way to pick the, anyway. Okay, so this is 1.96. What is M? M is the margin. But I didn't read anything about a margin, did I? It does say width of 2. So if the width is 2, then the margin mathematically, this is what I want to demonstrate. So the width is 2. So the width is 2 of an interval. So the interval, remember, is going to be like, with the mean here, then I'm going to go plus or minus from the mean. So this whole thing would be the width, but each of these are the margins. So a width of 2 means, this is all very dull right now, but it'll all be relevant when you start solving problems. So make sure you write this down. Width of 2 means 2 margins. So margin must be 1. And it's 1, it tells you 1 percentage point. So 1% is 0.01, okay? Now we have no information, no prior information is provided on a proportion. Like there's no other studies that are mentioned. You have no prior information. So we will just use, just revealing, there's nothing here about a previous study or a belief or anything about what P, the proportion of Canadians who understand the Constitution, actually is. So in this case, there's no prior information. I'm just going to use P of 0.5. 0.5. So we're going to write 0.5. Okay, so with these information, these data, these parameters, I'm going to put those in the formula and solve the formula for this sample size. So we're not done yet. Punch that in. Punch all that in and see what you get. So I'll give you a minute, okay? Give you a couple minutes. Did you get an answer? I'm going to shrink this and compute. So n is equal to 1.96 over m, which is 0.01 squared times 0.5 times 0.5. When you punch all that in, what do you get? Anybody got it? Anyone? The answer is, punching all that in, is 9604. Very good, 9604. 9604. All right, so now we have the answer exactly, but we have to choose among the options. So let's see which is the best option for 9604. Well, I think it looks like the other ones are way off. E looks like the right answer, doesn't it? About 10,000, right? It's almost 10,000. So I'm going to ask a question. So you did get this right, but what if I asked a question? Let's say I asked the question differently. What if E was not about 10,000? What if E was let's say that this said about 9,700. Let's do this below. Let's do this below with the number. What if you had to choose between $9,600 and 9,600? If you had to choose between those two alternatives, which one would you choose? Which one would you choose? Think about it for a moment. This is really important to drive this point home that I'm going to make. You know what I'm going to do, because I went over a bit, and I know I owe you another 10 minutes, but I need to go. I need to get going, actually. I'm going to leave this with you, and we're going to open tomorrow's lesson with this question, and I'm also going to finish the first row of the formula sheet number 4, okay? And just think about it and see if you have an answer for me tomorrow, all right? Also, send me questions on SDS, sampling distribution of a statistic. And unless you have any pressing problems, I will see you tomorrow. So just try that. We'll talk tomorrow. Okay, good night.